Welcome to the introduction of Fusion Compiler DFT synthesis training. The target audience of this training are for design and test engineers who may need to identify and fix DFT violations in either the RTL or gate level designs. After that, inserting scan into the system on chip designs, and then export design files to ATPG and PNR tools in the Fusion Compiler synthesis flow. At the end of this training, you will be able to execute the entire scan insertion flow in Fusion Compiler, including these steps: creating a test protocol for the design to prepare for DFT design root checking, perform design root checking at the pre-DFT and post-DFT stages, recognize common design constructs that could cause typical DFT violations, implement the top-down and bottom-up scan insertion flow, insert on-chip clocking controller for use at speed testing, and optionally include DFT-Max or DFT-Max Ultra compression structures. The prerequisites for this class are as follows. You should be able to open an existing block in Fusion Compiler which has been run through the logic opto stage of Compile Fusion, or alternatively, you can invoke and perform design technology setup and run Compile Fusion to logic opto in Fusion Compiler. You need to know Linux environment for the lab work. Some prior knowledge of design for test and scan insertion is useful but not required. Here's the agenda of the whole Fusion Compiler DFT synthesis class. First module, we're going to talk about what is scan testing and the scan insertion flow. Then we'll dive into the test protocol generation and how would you specify signals in order to generate the test protocol. Then we talk about test design root checking in Fusion Compiler. We go a little bit about the debugging design root checking violations in a graphic user environment. We'll then discuss some design root checking fixing to design to make a design more testable. We'll then look at a top-down scan insertion flow going from post logic opto through insert DFT and the rest of the flow. Some advanced scan insertion topics, including partitions, DFT partitions, will be discussed. We'll then talk about a bottom-up scan insertion flow. What are the considerations, and what data models will be needed in order to accomplish this. We'll then talk about exporting the data to other tools downstream, namely automatic test pattern generation, ATPG, and place and route tools. We then talk about on-chip clocking structures, inserting OCC controllers so that you can test your design at speed. We will then look at Synopsys compression technology, inserting DFT-Max and DFT-Max Ultra structures into your design to improve test time. Some advanced topics we're going to talk about are core wrapping and multi-voltage designs. And then we'll wrap up the training. So what is design for test, or design for testability? Design for testability, or DFT for short, involves extra design effort invested in making a chip more testable. What it does is it includes inserting or modifying your existing logic, and DFT techniques can be applied either in a structured way or an ad hoc manner. With the current complex SoC designs, DFT is pretty much structured and highly automated, with very little intervention by the designer. Each design is checked against a set of DRC rules, and any violations that the tool will see are corrected by either adding or modifying logic. So one of the very common example of structured DFT is scan path insertion. So the tool will insert a scan path by connecting all your sequential elements into a shift register kind of structure, and they're automatically routed independent of design details. Sometimes users may still want to use ad hoc DFT, and for example, sometimes testability logic will be added by the user, such as control or observe points, and location and type of these ad hoc DFT depends on the DFT savviness of the designer. Synopsys TestMax family of products deliver capabilities in 6 main areas. TestMax FUSA delivers functional safety and reliability analysis. TestMax Advisor in DFT performs powerful accessibility analysis and compression and integrating into synthesis flow. SMS and XLBIST provides memory test and repair and X-tolerance logic BIST and access. ATPG and diagnostics includes machine learning enhanced ATPG. ALE provides for adaptive high bandwidth test. And VTran provides pattern conversion for any ATE that you may be using. So TestMax DFT is Synopsys' advanced test synthesis solution, which is invoked from within Fusion Compiler. The key benefits of TestMax DFT are its transparent DFT implementation from within the synthesis flow. It accounts for testability early in the design cycle at RTL, and removes unpredictability on the back end of the design process, and achieves predictable timing, power, and signal integrity closure concurrent with test. Some of the key features of TestMax DFT, which are covered in this workshop, are DFT-Max scan compression technologies, hierarchical or bottom-up scan synthesis, automatic and manual test point insertion, call wrapper insertion with register reuse, and physical scan ordering. So Fusion Compiler shell can be run interactively or in batch mode. Typically, user might use it as a shell in a shell terminal. Graphic user interface is also available for the users to visualize and analyze the design, and DFT makes use of it. The major support channel for Synopsys EDA tools is through SolveNet Plus. Here is the screenshot of the web page as you log into the site. At the top of the page, you can search for documents and articles. If you file cases, you can manage it through this menu. You can browse through our documentation. You can get training resources. You can get software downloads and release notes, as well as methodology. As well as if you need to upload your test cases to Synopsys, you can go through these EFT or electronic file transfer. These are the icons used throughout this training. There could be recommendations. There could be cautions where the tool may behave in not intuitive ways, something to avoid, as well as some lab exercise as appropriate. With that, we will proceed to the first module. Welcome to Module 1 of Fusion Compiler DFT Synthesis Training. This module talks about scan testing and flows. After computing this module, you should be able to explain what the D algorithm is and use this algorithm to generate a pattern that detects a given stack fault in a combinational design, and do the same in a full scan sequential design. We'll talk about why scan chains are necessary to support automatic test pattern generation, or ATPG. Then we list the various Fusion Compiler scan insertion flows. We break this module down into these topics. We first talk about design for manufacturing test. We then talk about the fault detection process using a D algorithm. Then we talk about Fusion Compiler scan insertion flows, and then the basic steps in a typical scan insertion flow. What is manufacturing test? The purpose of the manufacturing test is to detect any manufacturing defects in an integrated circuit or chip that has been introduced during the manufacturing process. So the way that it operates in a high volume production environment is these chips, which were already packaged, is inserted into automatic test equipment. Then the test program written to detect such manufacturing defects will be run on the ATE. If the chips pass this test, then it will be shipped to the customer. If they fail the test, then obviously they won't be shipped. So what is a physical defect? Physical defect is an on-chip flaw introduced during fabrication and packaging of an individual ASIC or SoC that causes a device malfunction. So what are the common physical defects that we've seen? A design could have a short circuit, or could have open, or sometimes the transistor is always on. So basically, any of these defects would cause the chip to malfunction and not achieve its purpose. Many of the defects behave just like a permanent short to power or ground. So this kind of defects would cause input or output pins to appear stuck at 0 or 1. The input-output stages of most of the CMOS gates are patterned after the basic inverter, such that this simple model of an input-output pin stuck at 0 or 1 is widely applicable. The stuck at fault model is still the most prevalent fault model in use today. So the assumption is defects could happen at random locations throughout the die. So a stuck at fault model, by looking at a short or an open, where a input or output node is stuck at 0 or 1, would help detect such manufacturing defects. Now, other fault models do exist, but the key advantage of the stuck at model is its simplicity, and it significantly reduces the complexity of CPU-intensive ATPG algorithms. In a packaged integrated circuit, unlike a printed circuit board, you don't have access to each of the nodes on the design. You can only probe the design from the ports at the package level, from input to output. So what we mean by a primary port is an I/O port that has direct access to an external ATE hardware. Next, we'll talk about fault detection process using the D algorithm. Let's take a look at this simple example of combinational logic and how to perform stuck at testing. If the stuck at 0 fault is not present at this output, then this node can be driven to a 1. Else, if stuck at 0 fault is present, this node will always remain at 0. This if-else behavior can be used to detect the fault using the D algorithm. So in order to detect a faulty value, the D algorithm says we need to drive the fault site to the opposite value. So in the case of a faulty value of 0, we need to try to drive this node to its opposite value, which is 1, and therefore the top level port E needs to be driving a value of 0. Once we have determined the input value of a port to drive a specific fault to the opposite value, we need to be able to propagate this error to a primary output. The fault may be inverted along the propagation path. However, as long as the discrepancy is maintained, the fault can be observed and detected. Here's an example test pattern that would help detect a stuck at 0 fault at this node. The input stimulus might look like this, and if the design performs without any problems, we should see an expected response of 1. If on the tester we do not see this expected response, we can assume that the node in question does have a stuck at 0 and therefore has a manufacturing defect. So a test program for a complete design would consist of a sequence of these vectors, one of which could be used to detect the stuck at 0 fault at this particular node. So let's do an exercise. Instead of a stuck at 0, we want to detect a stuck at 1 at this node. What should the test pattern be, both the stimulus and the response? So the solution is to drive the input ports with this combination of inputs, stimulus. Note that the output may not depend on certain inputs, and some outputs we need not observe in order to detect a stuck at fault in a particular internal node. The goal of manufacturing test is to make sure that no defective products are shipped to your end customers. For chips that fail any test, you will not be shipping to your end customers. However, there is also a case where the parts would pass every test but still have undetected defects that could reach your users. Too many test escapes would undermine the confidence of the end user in your products. So the percentage of parts shipped with defects to users is determined by the defect level. Defective units can go undetected if the test program coverage is less than 100%. A high test coverage is needed to keep defect levels low. You need to make sure that as few end products have test escapes as possible. We just saw an example of combinational logic using the D algorithm. However, can the D algorithm be also used to handle flip-flops? You will still need to activate the fault and propagate its effect, and you will require the same ability to control and observe that is available in a purely combinational design. If you replace each register with a testable flip-flop, this replacement allows serial loading and unloading of bits. Here is a design of a scannable equivalent for an ordinary D flip-flop in the multiplexed flip-flop scan style. The cell has a multiplexer in front of the storage element. The functional path D propagates to the register when the scan enable signal is deasserted. When scan enable signals is asserted, the scan in pin value propagates into the storage element. So this scan equivalent flip-flop has a serial path going from the SI pin to the SO pin. This path is enabled only during scan testing by asserting the SE signal. Concatenating a series of scannable equivalent flip-flops, we can then form a shift register like this, which is also known as a scan chain. So the full scan strategy demands that all sequential elements to be replaced with its scan equivalent and connected them into a scan chain. A serial path is stitched through all the scan flops, therefore enabling the tester to preload the registers to a known value and capture the response from the output. The sequence of scan testing is also known as a test protocol. Let's say we're targeting this fault here. The start of the scan testing sequence is to shift a known value through the scan chain from the SI port. By pausing the clock, the scan data would propagate through the scan chain like this. Then the scan enable signal is deasserted and the functional clock is paused once, thereby propagating the value from this register to this gate. Then scan enable is asserted again, and the response will be captured by each of these registers and shifted out to the scan out. In the meantime, the next test pattern will be shifted in from the SI port. The scan load for a given pattern overlaps the scan unload of the previous patterns for all but the first and last patterns of the test program. You will see the overlap in this segment. Let's move on to the Fusion Compiler scan insertion flow. There are two types of DFT flows supported in Fusion Compiler, top-down and bottom-up. Top-down means that the scan insertion is performed at the top level for the entire design in one step. Bottom-up flows, scan insertion is performed at the block level, and the results are later combined at the top level. This diagram shows the difference between a top-down flow and a bottom-up flow. In the top-down flow, you'll be using a single DFT setup and perform scan insertion at the top level once. Depending on the design strategy, this may work fine. However, in some situations where the design is so large that the designer may decide to use a divide and conquer strategy and break the design up into blocks, in which case you may utilize the bottom-up flow to perform block-level scan insertion for each of the blocks, generate the handoff data, and then do a top-level scan insertion or integration. Now, let's talk about the basic steps of a typical scan insertion flow. Here are the steps of a Fusion Compiler scan insertion flow. After the design has been set up, you will open a design that has been produced by Compile Fusion to Logic Opto step using the commands openlib followed by openblock. Scan insertion is performed on mapped designs. The test protocol here will describe how the design operates in the scan mode. The signals involved in the test protocol are declared using the setDFT signal command. There are various commands that would control the scan architecture, such as number of scan chains, how the clock domains are handled, etc. You will specify this at the step called specify scan architecture. The commands primarily used to control scan architecture are the scan configuration and scan path commands. Once you have finished specifying the scan architecture, you would then generate the test protocol by using the command create test protocol. Once the test protocol is generated, you use the DFT-DRC command to perform design rule checking prior to scan insertion. If there are violations detected by the DFT-DRC stage, you could either reread the design or respecify some of these parameters and regenerate the test protocol. Once DFT-DRC results are clean, you will then run the preview DFT command to get a preview of the scan architecture before it is actually implemented in the design. This allows you to preview how the design might look like before actually committing the design changes. After scan insertion, DFT-DRC checks can also be run to validate the scan chains traced properly. DFT-DRC command can also be used to get an ATPG coverage estimate for the design that you've already inserted scan. The handoff files need to be written to disk that will be needed later in the design process. For example, you may want to write out the design block in binary format, or Verilog netlist ASCII for verification, a test protocol file for ATPG, test model files are for bottom-up flows, and a scandev file for external scan chain reordering. Here's an example scan insertion script. You start with opening the library and opening the block, setting the current block to the design under test, specifying the clock signals and resets, and then specify the necessary scan-in and scan-out ports, and then specify the scan configuration. In this example, we'll be specifying the chain count. Once the DFT specifications are complete, you will then run the sequence of commands create test protocol to generate a test protocol, running DFT-DRC before scan insertion to check for violations on individual registers to make sure that they can be stitched to scan chains without issues. Use the preview DFT command to have a look at how the post-DFT design might look like before committing the changes using the insert DFT command. Once DFT has been inserted, you can run the DFT-DRC command afterwards for post-DFT checks. Optionally, you can use the dash coverage estimate option to check for ATPG coverage. Various reports can be written after insert DFT, as well as any handoff files that are needed for downstream tasks. To summarize this module, we have explained how to use the D algorithm to generate a pattern that detects a given stuck-at fault in a combinational design. We then extend this concept to a full scan sequential design. We have explained why scan chains are necessary to support automatic test pattern generation, and we have listed the two Fusion Compiler DFT scan insertion flows. Hello, welcome to Module 2 of Fusion Compiler DFT synthesis training. In this module, we're going to talk about the test protocol. So after completing this module, you should be able to describe the elements that are included in a test protocol file. You should be able to declare constants, clocks, resets, scan-ins, scan-outs, and scan-enables to Fusion Compiler DFT tool. You should be able to name at least 2 Fusion Compiler DFT user interface commands. You should also be able to create the test protocol and modify, if necessary, to include a custom initialization sequence. So in this module, we're going to break this down into these subsections. We're first going to talk about test protocols in general. Then we talk about the DFT signals for the tool. Then we talk about the timing of signals inside the test protocol. Then we move on to creating a test protocol in Fusion Compiler DFT. Lastly, we're going to talk about controlling internal signals in the test protocol. But first up, what is a test protocol? The test protocol explains how to control the design in test mode. For instance, clock signals that need to be set up in order for the scan chain to shift. Perhaps you have some constraints such as scan enable or test mode signals, or perhaps you have to disable some asynchronous reset signals in order for the scan chains to shift. The test protocol needs to be created prior to running DFT operations such as design rule checking, previewing the scan chain architecture, and actually inserting the scan chain architecture. So if you look at this flow diagram, when you invoke Fusion Compiler, after you just set up the library and reading in the design, you will specify the scan architecture using Fusion Compiler DFT commands. The first command that you would do is to create the test protocol such that design rule checking can proceed. If everything is clean, you would then proceed to preview the scan architecture. Afterwards, you would run a command to insert the actual DFT architecture. Finally, you will be able to run a checking to look at the coverage that you've achieved. If, for instance, right after create test protocol, before previewing the design, you see any violations, perhaps you may need to update the design, or perhaps you want to change the architecture. Similarly, if after scan insertion, if there were violations that may need changing the design, or perhaps you've seen areas of low coverage, you may need to do a modification at the beginning as well. Here are the steps for creating a test protocol. You would first use the setDFT signal command to declare the scan signals, clocks, resets, constants, etc. Once you finish declaring all the signals, you would then use the command create test protocol to create the test protocol. The test protocol is described in the style or standard test interface language format, and therefore we commonly refer that to as a style protocol file or SPF. So in this training, we could be using this acronym SPF interchangeably to test protocol. Next up, we're going to talk about the DFT signals that are used in Fusion Compiler DFT. The setDFT signal command is used to define signals that are required for the test protocol. So the main command is setDFT signal. The -view option declares whether a signal is seen as an existing DFT or is it a spec view. -type indicates to the tool what kind of signal type it should be. -port is the list of ports that have this signal type applied to. -active state, for some signals, you may need to declare whether something is active 0 or 1. The -hookup pin indicates whether something is an internal pin. And the -timing option is for signals such as clocks or resets that may have some timing associated with it. Let's dive deeper into views. So Fusion Compiler DFT used two different views with setDFT signal command to define how DFT signals are be used by DFT-DRC command or insert DFT command. So setDFT signal -view existing DFT indicates that these DFT signals are already connected in the design, which must be understood for the design in order to pass DFT-DRC. So types such as clocks or resets. The -view spec are for DFT signals that Fusion Compiler DFT will use during insert DFT command when making new scan connections. Types such as scan in, scan out, or scan enable. So the default view is -view spec, meaning that you would define any specifications that the tool will make to connect the design. Report DFT signal command will display both views by default. So there are many types of DFT signals that you need to define prior to scan insertion. These types such as scan clock, reset, constant, scan data in, scan data out, and scan enable. For a signal to be declared to Fusion Compiler DFT, the port must exist in the current design. The existence of a port doesn't affect the views to be used when declaring the signal. So for instance, I may have a scan data in port that is existing in the design, but it has not been connected, so therefore I'm still defining that as -view spec. One footnote on ports is typically the DFT signal refers to a top-level port. However, it is also possible to define a DFT signal and an internal pin. We're going to talk about this later on. So let's start with the first signal type, which is a scan clock. By default, the test period is 100 nanoseconds. You can change the clock period by using this app option, dft.test_default_period. Then you use the setDFT signal command. Here we use the -view existing DFT because this is an existing functional connection. Then you use the -type scan clock. Let's say I have a port called clock, and the timing is rising at 45 nanosecond and falling at 55 nanosecond. So this is the command that would declare to Fusion Compiler DFT that I have an existing clock signal driving these registers in my design. Here's some additional information on setDFT signal -timing option, which is used to define the timing and waveform for a clock signal. The -timing option accepts a list argument with two values corresponding to the rising edge and falling edge. So the first argument is rising, and the second argument is falling. So in this example, I have rising at 45 nanoseconds and falling at 55 nanoseconds. So as a result, I have defined a return to zero waveform. In the second example, if my rising is at 60 nanosecond, but falling is at 50, that means the rising comes after falling, which means that I have defined a return to one waveform. The next signal we want to define are asynchronous resets. Again, we'll be using the -view existing DFT because typically the reset signals are already connected for functional purposes. So you would use the command setDFT signal -view existing DFT -type reset. Here, my example port name is reset n, and the active state is 0 because all these signals driving the registers have the active state 0. Fusion Compiler DFT treats both clocks and asynchronous resets as clocks in the test protocol. This is due to DFT-DRC engine treats that any signals that changes the state of a register is classified as clocks. Next up are constant value signals. So let's say I have a mode signal here that I need to constrain such that the reset signal will reach the registers here. So again, I'm using setDFT signal command -view existing DFT. Here, the option is -type constant, defining the port. And here the active state is 1 because in order for the reset signal to pass through the mux and reaching the registers, I need to constrain the signal to 1. Let's now define some signals in the specification view or view spec. First up is scan data in. So I will use the same command, set DFT signal, -view spec, because there's no existing DFT connection, new connection to be made by insert DFT command. Signal type is scan data in, and let's say I have a port test_SI. If I finish that dash port option, DFT will connect directly to the top level port, which is test_SI. However, let's say I have an IO pad, U1, and I want the tool to connect to the output of this IO pad. I can optionally specify the hookup pin to tell the tool, please connect to the output of this pad as the scan data in signal. So similarly, for scan data out, again, I'm using -view spec. The signal type is scan data out. Let's say I have a port called test_SO. So again, I could just stop at the dash port option. Or if I have an IO pad, I can also specify the dash hookup pin to be the input to this IO pad and define that as a hookup pin for the tool to connect to. Next up are scan enable signals. So scan enable signals are a little bit special. It could be used by both design route checking as well as DFT insertion. So in this example, I have a clock gating cell, which I already have a scan enable signal connected because I needed to make the clock gating signal transparent such that the clock signals will reach my registers. So therefore, I could use the -view exist to specify any existing functional connection to the clock gate pin. However, I will also use the -view spec to indicate to the tool that there are new connections to this SE pin that needs to be made. So therefore, I will be specifying both view spec and view exist on the same signal. So notice that in the view spec, I could be defining an additional hookup pin option to tell the tool that it should connect to the output of this pad. Otherwise, the tool could connect directly to the top level port. After the previous example, you may question, well, when should I use -view existing DFT and when should I use -view spec? So rule of thumb are signals that need to be identified for DFT DRC should use the -view exist option. So some examples are scan clocks for MUX-D scan style. I may have a reset signal, asynchronous reset or set signal that needs to be informed to the design route checking engine. I may have a constant signal, as well as a scan enable as a test pin for clock gating. So these are the types that I would use for using the -view exist. In addition, if you have an LSSD scan style, the A clock and B clock should also be defined with a -view exist with these two different signal types. As for view spec, the rule of thumb is the signals that need to be connected by the insert DFT command, you should define it using the -view spec option. So signals such as scan input, scan output, and scan enable should be defined using the -view spec option. If I have a test mode signal for DFT max compression or on-chip clocking controllers, you will also use the -view spec -type test mode to define a port that needs to be connected as a mode selection using the insert DFT command. In addition, for LSSD scan styles, the A clock and B clock ports to be stitched should also have a -view spec option. So putting all these commands together, let's take a look at this example script. So we start out with opening a library, analyze my RTL and elaborated the design, specifying the scan style, and then I map the design to gates using the Fusion compiler to logic opto option. So first up, I define my existing DFT view signals such as clocks and resets. With that, I can run create test protocol and DFT DRC command to check whether my registers are scannable or not. Notice that you must define existing DFT signals prior to running the DFT DRC command. I then define the spec view signals using the set DFT signal -type scan data in, scan data out, or scan enable. Notice that I did not specify the -view spec because that is the tool default. These signals need to be specified prior to insert DFT. In a typical example, or for readability purposes, you may put all the set DFT signal prior to DFT DRC command. So let's say in this view spec settings, I could combine them and put them all before DFT DRC command. Next, let's talk about the test protocol timing in detail. The test protocol includes timing and event order to be applied on the ATE. So in this example, we are defining the clock at 45:55, rising and falling, and the tester will strobe or check the output of the design before the clock rising. This is known as a pre-clock measure timing, and is the default in Fusion compiler. The pre-clock measure is the default timing used by Fusion compiler DFT and TestMax ATPG. The pre-clock measure timing is where in the ATE cycle, it would force the primary inputs at the beginning of this clock cycle. It first measures the primary outputs and then pulses the clocks. The event order is determined by the DFT.test default options as well as the scan clock timing. Next, let's talk about creating the test protocol. Once you have defined the signals and timings, you can use the create test protocol command to create the test protocol. And once this has been created, you can write the test protocol out to disk using the write test protocol command. In Fusion Compiler, the test protocol is written in style format, and therefore we usually refer to test protocols as style protocol file, or SPF. Here are some of the structures or keywords that are contained in the style protocol file. First of all, we have some headers and comments. You will have a top-level signal declaration. If the design has already scan stitched, you will see a scan structures section. You will see timing information, some procedures to describe how capture, load and load, and shifting occurs. And then last up is an initialization sequence, encapsulated in the macro defs section with the keyword test_setup. Let's take a look at a test protocol file for a simple design. Let's say I have these input and output ports, and the signal groups are defined according to the purpose of each of these signals. For instance, I have specified SI and SO to be scanned in and scanned out respectively. _PI would be primary input for all my signals in the design. _PO will be primary outputs. And in this case, all inputs and _PI are pretty much the same. Similarly with all outputs. Now, in this design, I already have a chain stitched. So the scan in and scan out are already defined here in the scan structures section. I could have different waveforms defining in the timing section. I then define the procedures in this test protocol. So the first procedure are captures. So this is the sequence in order to perform capture. I need to constrain the test mode signal using the F keyword to say that during capture, this signal needs to be 1. I then use the V keyword to indicate that the vector to be applied and sampled. The pound or hash character is a placeholder for ATPG. Load and load section is to indicate how to shift the scan data through scan chains. So I'll be using W keyword with the timing waveform table. C indicates conditional values. V is for vectors. And the shift sequence looks like this. I will need to pause the clock and then apply scan in and sample scan out data. So again, the hash or pound character are placeholders for ATPG. Next up is how to control an internal signals in the test protocol. So in your design, you may have some internal nodes that must be initialized for a design to pass DFT-DRC. So how would you initialize these internal nodes? You could define a custom initialize sequence in the test protocol by modifying the test setup macro. Alternatively, you can define a signal using the internal pin specifications where the DFT signal is defined as an internal pin using the set DFT signal command. Or you can define to the tool that's the mode assumptions using the set test assume command. The recommended method is to use an initialization sequence whenever possible, so is item 1. The read test protocol command -section test setup option can be used to load a sequence of vectors in order to place the design in the desired state prior to running DFT-DRC. The create test protocol command automatically writes out a very basic initialization sequence in the test setup section. So in this example, it first constrains the clock to the off state, and then the next vector, it will apply the asynchronous sets and resets and force them into the inactive state. Also, the test constant signals that need to be constrained at the end of the initialization sequence will also be applied. However, for a more complex initialization sequence, it's up to you, the user, to define this custom sequence. Here's an example of using initialization sequences. Let's say I have a DFT control module that I need to generate a test mode signal driving downstream registers. The initialization sequence is such that I need to propagate this value of 0, 1 through these two registers. So I can define a test setup sequence with the necessary waveform such that at the end of the initialization sequence, the signal CRE is set to the constant state at the test setup procedure. I then use the command set DFT signal -port CRE active state 0 to indicate that the end of the sequence needs to be at value 0. I then use the read test protocol command -section setup to read in the initialization sequence. After that, I use the create test protocol command to build the complete test protocol, and then run DFT-DRC command to perform design root checking. So here's the flow to create an initial protocol file to modify the test setup. So you first define all the DFT signals using the set DFT signal command. You then use the create test protocol command to create the initial protocol, then use the write test protocol command to write out the protocol to disk. Afterwards, you use a text editor to modify the test setup section of your test protocol file. Once you finish that, in a separate DFT section, use the same DFT signal definitions, and then use the modified initialization sequence, and then use the read test protocol -section test setup option to read this modified test protocol. Afterwards, you again run the create test protocol command to generate the rest of the protocol, and then run DFT-DRC command to check the design rules, and then finally use a write test protocol command again to write out the new test protocol. So remember to always do a create test protocol command after reading the test setup section. Alternatively, you can use the internal pins flow to bypass initialization. You might use this flow when in a situation where, let's say, the DFT controller is still under construction, but you needed to perform scan synthesis for the downstream registers, and the DFT controller, you can assume that the test mode signal generated is going to be a 1 after the initialization sequence. So you can proceed with the set DFT-DRC configuration -internal pins enable option to enable the internal pins flow. After that, you use the set DFT signal command to define any signals that need to be constrained to a particular value by specifying set DFT signal -view existing DFT -type constant. And here I'm only defining the -hookup pin option without defining the -port option. So in this example, I have defined each of these registers to be of a different active state. The third way to bypass initialization is to use the set test assume command. So the set test assume command can also be used to set a logic value on an internal node of a design. So in this same example, I am using the set test assume with the active state value and then the node that I needed to constrain to. You can then use the report test assume command to report any assumed signals. A word of warning in test protocol file written out with the internal pins flow. The test protocol file written out with the internal pins flow enabled cannot be directly used in TestMax ATPG. You will have to modify the test protocol file to specify the relevant top-level ports, constraints, or initialization sequences that are required to enable top-level controllability. So think of running TestMax ATPG as applying signals at the chip package. You have no access to internal nodes of a design. You will have to write the proper initialization sequence applied from the package pins in order to initialize your design. The same warning would apply to protocols where set test assume command was used for DFT-DRC. So to summarize, you should now be able to describe the elements that are included in the test protocol file. You could declare the constants, clocks, resets,